In this video, we consider potential extensions of the GARCH model. Recall that the standard GARCH model has that the conditional variance sigma t squared is symmetric in epsilon t minus 1. So it means that the sign of the shock at time t minus 1 does not matter for the volatility at time t. So we can simply see that if we plot sigma t squared as a function of epsilon t minus 1. We get this red curve here, and we have symmetry. But one may actually think about the case where the impact of the shock depends on the sign of the shock. So one motivation could be that if we have a large unexpected negative shock, that this should have a greater impact than a positive shock. One example of such a model is the so-called threshold asymmetric model. So compared to the standard GARCH 1.1 model, we have an additional term in the threshold model. We have this term here with a kappa times the squared lagged shock times the indicator function that this lagged shock is negative. So this indicator function here means that it takes value 1 if the shock was negative or 0 otherwise. And here kappa is a non-negative constant. So what this means is that if the shock at time t minus 1 is negative, then we have a larger arch coefficient, namely alpha plus kappa, compared to the case where the shock was positive and where we only have alpha as the arch coefficient. One can show here that if Zt is symmetric, then the stationarity condition for this model here is that alpha plus beta plus a half kappa is less than 1. We can try to estimate this model here based on the S&P 500 data. So again, we include 2 lags in the conditional mean equation. Now we estimate a GARCH 1.1. Let us stick to the non-normal error distribution such that we have that the conditional distribution is assumed to be scaled students t. Then we can simply choose here the threshold GARCH, which is the asymmetric model. So later on in this video, we will also consider the so-called asymmetric GARCH model. And if you want to estimate that, you should simply click here instead. And note we can also estimate a combination of the two models if we want to do that. Likewise, we will also consider the so-called GARCH in mean models. So here the conditional variance enters in the conditional mean equation for yt. And we can choose different specification of this kind of model if we want to. In the video, we will consider the specification where we have the log of the conditional variance entering the mean equation. So we get the following output. Note here that we still have these AR terms, where the first term here appear to be significant, whereas the second lag here appears to be insignificant. Quite interestingly, we note here that alpha 1, which corresponds to the alpha coefficient in the model, so the usual arch coefficient, is actually found to be equal to 0 for practical purposes. So it means that our estimate of alpha is 0, but we still have arch effects through this threshold parameter, namely the kappa parameter, and then we see that this is highly significant and positive. So what this suggests here is that the conditional variance does not react to positive shocks, but only reacts to negative shocks. So we have a huge degree of asymmetry in this case, and I actually plotted the news impact curve for this model. This is the blue line here. So we can see here that the volatility or conditional variance reacts more to a negative shock compared to the baseline standard GARCH model, whereas it doesn't react at all to positive shocks. So we have a high degree of asymmetry. Another potential extension of the model is the so-called asymmetric model, where the arch term is so to say shifted. So instead of only having epsilon t minus 1 squared, we have epsilon t minus 1 minus gamma for some parameter gamma that we want to estimate. The main motivation here is that the a zero-valued shock is not neutral to the news impact curve. So in particular, it means that a shock that equals gamma, where gamma could be positive or negative, is the neutral shock. Again, we could estimate this with the PCGIF package, and we get the following estimation output. Here we get a gamma that is around 0.5%. So this suggests that if we have a shock around 0.5%, that this is neutral in terms of the news impact curve. We can see here that the gamma is also highly significant, so it indeed suggests that we have a significant asymmetry effect here, and we have the news impact curve again, which is given by the green curve here. So again, we can see that the neutral shock is around 0.5%, and we can see that the conditional variance reacts more to a negative return or a negative shock compared to a positive shock. Another model not dealing with asymmetries is the so-called GARCH in mean specification. So the idea is that standard finance theory suggests that there should be a trade-off between risk and return. So ideally, if an investor takes up more risk, he should be compensated by this by getting an expected higher return. So one could model this directly by stating that the conditional risk or conditional variance should enter in the conditional mean equation for the returns. So here, in addition to the usual xt prime theta term in the conditional mean equation, we could have a term here with delta times sigma t squared. We could also have the conditional standard deviation instead, or the log of the conditional variance if we want to do that. The interpretation is that this delta here reflects a risk premium, and we can estimate this model here, and we find that there is a positive risk premium if we choose this log of the conditional variance in the conditional mean specification. So it suggests that the conditional mean is increasing in the conditional variance. So indeed that there is a risk return trade-off. Some other extensions we will not discuss in detail here, but are considered in the lecture notes, is the so-called eGARCH and the GARCH-X models. So the eGARCH model is a model for the log conditional variance instead of the conditional variance. This model has some appealing features, namely that we don't have to restrict the model parameters to be non-negative, and moreover it automatically accounts for asymmetries. We could also consider a model, the so-called GARCH-X, where there's an additional variable entering the conditional variance equation. So for instance, it could be that instead of having that the conditional variance is only driven by past shocks and past values of the conditional variance, there could be some say exogenous variable driving the conditional volatility. It could be a variable saying something about the state of the economy. It could be a so-called leading indicator. It could be credit spreads or some interest rate spreads, or something else, another measure of volatility. And so this is a highly popular model in applied work, and we can estimate such models if we want to do that.